Speaker is Reimers, who's going to tell us about modeling the electronic properties of porphyrins.
Ross gave me the challenge of talking about strong electron correlation in porphyrins, and I'm going to try and connect it into the theme of the conference on modelling big systems that involve. So I guess I'd like to start by thanking Ross and ICAM for the invitation to come here. It's lovely meeting. And also to acknowledge my co-workers, Professor Harsh and Professor Crosley, who made all the molecules. Max, incidentally, is Paul Byrne's PhD supervisor, is the connection between the last two talks. Also, Rika Kobayashi at Supercomputer Center at ANU, and Roger Amos, who did the DFT coding. And my postdoc, Singli Kai, Shui Yin, and Max Dahlbaum, and Peter Campfield, who's here with a poster on some of this work. Where are you, Peter? Outline of the talk is going back to undergraduate teaching material in chemistry, but this isn't not necessarily all that well known in the physics community on what's an aromatic molecule and what controls its spectroscopy. So that's called the perfect pairing theorem. And then once we understand aromatic molecules and their spectroscopy, we'll then try to apply that to porphyrins and chlorophylls. And then computational methods like density functional theory, once you understand the nature of the states in the porphyrins and chlorophylls, then you can work out whether density functional theory will work and give you a reasonable number if you're using it for those excited states. And then lastly, we'll apply it to exciton coupling in photosystem 1, where we're taking molecules which are internally strongly correlated, like chlorophylls, but are weakly correlated to each other. And then we're putting together a large macroscopic system of weakly coupled, strongly coupled systems, and show the mathematics of how you handle that type of electron correlation. The perfect pairing theorem comes from Coulson in 1940. Coulson was the person who wrote down all the analytical solutions to Huckel equations that everyone knows and loves, like the cosine band structure from tight binding theory. Coulson did all that work in the 1930s. This work here is on Alton, non-Alton hydrocarbons. So naphthalene and azulene here. What do I do? Okay. Naphthalene and azulene have the same number of electrons. They both should be aromatic according to Huckel theory. Only naphthalene is aromatic, however. Their chemical and their physical properties are completely different. So why is this? That's what Coulson was trying to understand. And for naphthalene, you can take every second atom and put a star on it. And so you can go around there, and no two of those green dots are on adjacent atoms. So any molecule with that property is called an alternative hydrocarbon. But azulene down here, you can't do that. There's no way you can do it without having two adjacent atoms here with the dots on it. And that's called a non-alternative hydrocarbon. And their spectroscopy and their chemical properties are just completely different. And the reason for that is that if you've got Huckel theory, tight binding theory, you've only got interactions between neighbouring atoms. And if you look at this atom here and that one there, all their interactions are perfectly symmetric. So the key elements then of the energy matrix for the two atoms will all be the same. And with Huckel theory, there's no interaction which takes you from that one over to that one. So there is, at a first order of approximation, if you're using perturbation theory to solve the Huckel equations, there is no interaction between the matrix elements on both sets of atoms. And so, as a result, you predict at first order perturbation theory expansion of Hooke equations, degenerate eigenvalues for the molecular orbitals. And the assumption that that is true is the perfect pairing theorem. Benzene obeys the perfect pairing theorem. It has enough symmetry to do such. You have here the Homo orbital, which is doubly degenerate, and the Lumo orbital, which is doubly degenerate. So this is a classic example of perfect pairing. Not true for all orbitals, for example, this one. Naphthalene, not quite the same. You have a Homo and second Homo orbital that are almost the same energy, and a Lumo and second Lumo that are almost the same energy. The perfect pairing theorem would say that they were degenerate. So they're close to being degenerate, so that's why perfect pairing is useful. Azulene, however, on the other hand, has an electronic structure more like an alkane than a ring system. It has a continuous band which runs across here, and so there are low energy transitions. And azulene, a very brightly coloured dye. The orbitals are opened up to chemical attack. So that's why azulene is very different. The perfect pairing theorem does not apply at all to azulene. Porphyrin, again, has nearly degenerate Homo and Lumo orbitals, so the perfect pairing theorem is working for porphyrin. How can it be working for porphyrin, when you ask, when there are 5-membered rings around here? How can you have atoms separated by 2 in a 5-membered ring? It's impossible. Well, the reason for that is that these 2 orbitals on the side here actually decouple from the rest of the ring system, and it's like they don't exist. And so you end up in porphyrin with an 18-electron ring system that runs around here that makes porphyrin an aromatic molecule at the lowest level of approximation. And at this level of approximation, it obeys the perfect pairing theorem. And that's hence the nearly degenerate pairs of orbitals. And indeed, if you go one step further, you make a metallic porphyrin where there's a metal sitting in here. So it's like benzene high symmetry. The Lumo becomes degenerate again in the porphyrin, so it's exactly holds to the Lumo, and very similar orbitals to the Homo here. This is the perfect pairing theorem. It controls all aromatic spectroscopy. All of these molecules except azulene have very, very similar behaviour. And how does that behaviour come about? This is what the perfect pairing theorem predicts for spectroscopy. If there's a degenerate Homo and a degenerate Lumo, there are 4 electronic transitions between the Homo and the Lumo. And 2 of those transitions will be polarised in one direction, here the X direction, and 2 will be polarised in the other direction, the Y direction. It's a planar molecule. And so the 2 X-polarised transitions, there's a strong interaction between those 2 transitions. This is the electron correlation between the 2. And that coupling, that interaction, is about 1 to 2 volts, typically, in an even hydrocarbon, alternate hydrocarbon. So the lowest excited state of the system is made up from the Homo. This is in terms of Hartree density functional theory, would be the Homo-Lumo gap minus the interaction between the electronic configurations with an antisymmetric combination of the 2 wave functions. Ben told me the word for that this morning. What was it, Ben? Entangled states. Quantum entanglement. Yes, thank you, Ben.
No, it's not entangled.
No, it's not entangled. So there's a plus and minus linear combination. These 2 excitations are phased. And the higher energy excitation, it becomes allowed. It takes all of the oscillator strength, and the low energy one becomes forbidden. And exactly the same in the Y polarization. And so there are no single excitation determinants possible for this system. This is the observed spectrum for porphyrin. Down here there are 4 peaks you can see at low energy. two of them are electronic origins and two are vibrational origins based upon the electronic origins. So I've only marked the electronic origins. And they're called QX and QY. And that's the two low energy transitions, the two forbidden transitions in the perfect pairing approximation, which should have no intensity. Well, that's the amount of intensity they have in reality. And the two high energy transitions appear degenerate here, and they're called BX and BY, or the Soré band of the porphyrin. And it has a vibrational structure sitting on the side of it here too. Now next here is called the N bands, and the N bands are very broad, and we'll come back to them later.
You just mentioned the little thing, the Guterman 4-orbital model. So these four,
right here.
the 4 orbitals.
Right here. Next slide.
Okay.
These are all the orbitals for the porphyrin that would come out of the molecular orbital calculation. And sitting there, these 4 orbitals, that's the Lumo, the second Lumo, the Homo, the second Homo. That's the nearly degenerate Lumo and the nearly degenerate Homo. Transitions from the occupied orbitals here to the virtual orbitals there give you the Q band and the Soré band. And that's called the Guterman 4-orbital model for porphyrin and chlorophyll, developed by Guterman in the late 50s, but it's exactly the perfect pairing theorem from Coulson from 1940. These exactly the same states appear in, say, naphthalene or the molecules we were seeing yesterday. The symbol singlet LA and singlet LB we saw yesterday. The same as the Q bands in the porphyrin, exactly the same origin in terms of the perfect pairing approximation. Now, the N bands were first assigned by Professor Hush in the 60s. And the N bands come from excitation of these 4 orbitals, that's the next 4 underneath the Homo and the Lumo, underneath the Homo, into the Lumo pair. But what we've only discovered recently, and this is still quite controversial, is that these N-band transitions are charge transfer states. Here we show the molecular orbitals under the influence of a very weak applied field in this direction. And the result is that these orbitals have localized onto the 2 pyrroles here. In no field it would look like this, delocalized over both pyrroles, but under a very weak field the orbitals localize. So if you have an excitation from this orbital into that orbital, it produces a huge dipole moment across the porphyrin. It's a charge transfer band. And that's why the band is so broad in the absorption spectrum, because charge transfer bands are broad. That feature was not really been realized. To show the charge transfer nature of these things, we plotted here, this is against electric field strength, and this is the transition energy. These are the observed transitions here. You're in 2 different polarizations on the top and the bottom. This is the lowest states calculated by a whole variety of methods. And in here is CAS-PD2, a perturbation-based ab initio method. And that shows you a Q band here, a Q band here, and here's the 2 Soré bands. And they're independent of electric field. They're the normal sort of transitions you expect on a porphyrin. But at higher energy here, here's the N bands, and they're responding to the electric field. That's because they're the charge transfer bands, and they're responding to an external field perturbation. But if you do density functional theory, and this is traditional density functionals, and all the latest ones like charge density functional theory, and so sort of the state-of-the-art density functionals from the last of the few years, they all have charge transfer bands. The N bands are all sitting amongst the Soré bands. And but there is a new density functional that's just come out called CAM B through LIP, and it gets it pretty much right. So it's the first density functional that can do porphyrins. For chlorophylls, you saturate this bond here, and the result is that the Y polarized states decouple. Not completely, but to a significant extent. So the QY band becomes intense in a chlorophyll due to this decoupling. But the coupling is still sufficiently strong that you have to treat both. You have to treat the singlet, the configuration interaction in proper calculation. And it's exactly the same story on the chlorophyll. There's the orbitals, there's the porphyrin 4 orbital model, and here's the end band of the chlorophylls. There's only 3 of them now because you've saturated this ring, so there's no virile excitation on that ring. But what happens if you try density functional calculations on this, it now puts the charge transfer bands down amongst the Q bands. So density functional theory basically gets chlorophylls totally wrong because you don't have the proper Q bands and sorate bands, you have charge transfer states that shouldn't be there at all. They should be much higher in energy, like this couple cluster calculation here. It's putting them up, sitting on top of the sorate band, which is about where they should be. But they shouldn't be down here amongst the Q band. Can be through that, again, gives a sense of my answer. So the last bit then of the talk is to apply this knowledge to look at exciton transport in photosystem 1, which is a condensed phase system where there's 288 chlorophylls sitting beside each other. We want to look at the exciton flow between the QY states of the chlorophylls. How do we expose these QY states to do the calculations? So Peter Canfield has a paper on this tonight. We optimised the structure of the whole system, 150,000 atoms using density functional theory, because the X-ray structure is useless if you're trying to calculate spectroscopy. We use both CAM-B3-LIP, the density functional that works for chlorophylls, and INDO, a Hartree-Fock semi-empirical scheme that incidentally reproduces the Kondo effect. This is a full CI program, it's a very powerful code. But what I'm going to show you here is how we used it with INDO, because the INDO program, you can get at all the inner workings of the calculation, whereas with a DFT code like Gaussian, you can't get at all the key numbers. So I'll show you here because with INDO, because it's exactly the same with Gaussian, if you can get the numbers. So we start with the 2 chlorophylls. We want to see what is the effective interaction between 2 chlorophylls, any 2 of the 288 chlorophylls in the system. And in the presence of neighbouring molecules that may be chromophores like tryptophans or carotene. So the questions that were asked yesterday is, does the protein have any role in mediating the processes other than structure, which Ken was asking about yesterday? If the protein does, we put it into the calculation here, because there is the electronic states of the protein acting on the transferring excitons. So what we do is we take the Fock matrix for the system, this is a Hartree-Fock program, and localize the orbitals onto the 2 chlorophylls and anything else without mixing the occupied and virtual blocks, so we don't change the spectrum that you calculate from this. It's just the way you interpret the spectrum. And then generate the single excitation CI matrix describing the electron correlation between all the possible states. But now in a basis set which describes excitation from chlorophyll A to chlorophyll A, B to B, and here's a charge transfer excitation from chlorophyll A to chlorophyll B. So we put together the full CI matrix and then diagonalize the diagonal blocks. Each block separately diagonalized, and the whole Hamiltonian transformed back into the eigenstates of the individual blocks. So what does that mean when you diagonalize this block here? This is all the excitations on chlorophyll A. It's like you had an isolated molecule. So that exposes the Q and the B and the N states are all exposed as eigenvectors after that diagonalization. And similarly, you do that to all the blocks, but down here is the eigenstates of chlorophyll B, and down here the states of the carotenoids or the tryptophans or whatever else that's in the calculation. And then after the back transformation, you end up, the diagonal blocks down here are diagonal, and the numbers along the diagonal are the energies of the excited states, the Q, QY, the B states of the molecule. But now, all these numbers down here, this, for example, if that's the QY state of chlorophyll A, if that's that basis vector, and down here is the QY state of chlorophyll B, this is the B to B block, then these numbers describe how the QY state interacts with all other states of the system. And then the exciton coupling constant, you may think it's just this number here. That's the through space term. But we also put in the super exchange terms which go through all the other states, giving an effective exciton coupling.
Is that the dexter? Is that equivalent to a dexter?
And Forster. It contains Forster, dexter, and everything else that those two exclude. It's everything. This is the last one. So then we can use that. We can model the spectra of photosystem 1, and these are the calculated curves which model the spectra, and then get out where all the different chlorophylls lie and how they contribute to the spectra. And from that, you can get also the rate constants for the exciton flow through the system using standard type binding type models for it. But you've got to handle the strong electron correlation first before you can do that. So, thank you.
Okay, so questions?
So in terms of bridging the language gap between physics and chemistry, generally in physics we would say that something is strongly correlated if it can't be written in terms of a single slated determinant.
Yeah, I'm using your notation.
Right. Okay.
Chemists would never have said that this system was strongly correlated.
But you would. But one of the main points is if you want to look at the electronic states of the porphyrins, that you have this 4-orbital, it boils down to this 4-orbital, and that has to be treated by configuration interaction. So in the physics language, that would be strongly correlated.
Right.
And one of the signatures you said that is it doesn't get the charge transfer states correctly.
Oh, the charge transfer states are states beyond the Guderman 4-orbital model. They're the next states. The next highest energy states are the charge transfer states. But the significance of them is that density functional theory gets their energy completely wrong, as it always does for charge transfer transitions, and it gets them too low. So if you try and do a calculation using DFT on chlorophylls, you end up with you see the fictitious charge transfer states, not the real states.
Can I ask a question? Why are they charge transfer states if they're states which are essentially lower? I mean, they're lower p-orbital states, aren't they, within the system? So is that right? I'm just trying to understand why it's not going to be a charge transfer.
So here's your orbital. This is the orbital you're coming out of.
Right.
So if you go from a localized orbital into a delocalized orbital, you've got a plus charge on that ring and a minus charge on the rest of the system. So you've induced a huge dipole moment into the molecule. So each of the 4 pyrrole rings are acting as independent ligands, if you like, on your metal complex. It's a ligand-to-ligand charge transfer band.
Yeah. And so why is it controversial?
Because no one's ever seen this before, and all the DFT people, they all reckon that DFT is wonderful for chlorophylls, and there's dozens of papers out there, and they're all crap.
Yeah, but I mean, there are certain experimental signatures for charge transfer states.
Yeah, they're all there.
And they're all there.
Yeah, it's just no one's ever seen them before.
So
the bands are solvent sensitive, they're broad.
yeah.
Back to the DFT, I don't know enough, but does normal DFT fail because of the long-range Coulomb?
The asymptotic potential area, yes.
So how do you fix that? Why does the CAM DFT actually work?
Well, it's beat 3 lips, so you put in the Hartree-Fock Exchange, so the exchange integral is much better represented, and that broadens the band gap. But at long range, that's bad news because you don't have... So the Hartree-Fock term is non-local, whereas all the other terms are local in a density functional, mathematically local. So even in a GGA, they're mathematically local. Yeah. So there's no term in the correlation energy which cancels the exchange energy at large distance. So you have a much better description of the system at small distance, but a poor description at large distance. So that's why B3 lip only does well for transition states, but doesn't solve the asymptotic problem. So in CAM B3 lip, the Hartree-Fock exchange is damped at large distance, going back to a GGA type functional at large distance. And so the errors are cancelling.
So it's sort of an
Yeah.
artificial
Yes.
manipulation of the errors.
Yeah. And there's no proof that it would... oh, yes, there is a proof that it's asymptotically correct. It contains the self-interaction corrections that all the other density functionals they put up there also include, but they don't get it right. Only this one gets it right. But it actually gets it a little bit too... The band gap is too big, slightly too big, so it's not perfect. There needs to be another iteration. But then a whole new classes of molecules will be opened up to density functional analysis when this is done. So it's a big thing.
I think probably may not be directly related to this. I noticed in the literature, Q-band, solid band, all very strong couples bonus that the internal conversion is extremely faster. Is it well understood or is still don't know? I mean, in 100%
Yes,
very
okay.
quickly internal conversion.
I think in porphyrins and chlorophylls it is not well understood because the systems are too big to find the conical intersections. The calculations that we're doing there are really pretty difficult. And they're not as difficult as the ones you're asking for. But if you go back to any of the smaller aromatics, benzene derivatives or indoles or naphthalenes, then all those things are mapped out and understood. But it is an area that needs a lot of work on in porphyrins and chlorophyll still is to do that. So, yeah.
So in this regard, I have is it like fluorescence from this porphyrin? Like
Fluorescence.
radiative transitions?
Yeah.
Is it well understood? Because it is going to fluoresce with the two
Yes.
bands around 600 nanometer.
The fluorescence is very weak. A strongly fluorescing porphyrin will have a 4% quantum yield of fluorescence.
Hematoporphyrin, porphyrin 9, which is normally used for this photodynamic therapy, is strongly fluorescent. Like quantum yield is 30%.
30%. Well, that's enormous for a porphyrin.
So that's what I'm asking. Is there any iteration that?
Yeah, I don't know. There are some porphyrins that have higher quantum yields. Maybe Prof. Hush knows the answer. I don't know the answer.
I mean, can you do the porphyrin diamond calculations? I mean, a lot of
Yes.
people used in clinical PDT are
Yeah.
diamonds.
Exactly.
Have you applied this to looking at diamond, absorption spectrum diamond?
Of dimers,
Diamond.
yes.
Because it can have the H and J ligands like that.
Yeah, this isn't fluorescence of diamonds, but this is the absorption of diamonds. This is a porphyrin dimer here, and this is its observed absorption spectrum. And this is what you get if you do a DFT calculation on it. You get hundreds of states in the Q-band, Sorry band region, and they're all charge transfer bands. But CAM-B3 gives you something which looks like the observed spectrum. So the absorption band we can handle, but we've never looked at the emission.
But I think the question is about whether or not you have dimers which are co-facial dimers
Okay.
rather than lateral dimers. There's no systems there. There's not a strong localization of the pi system across. Whereas with some of the other ones which are connected through the meso positions, they're much stronger.
Much stronger, yes. We've worked on meso-coupled systems and we've worked on pi-stack systems as well with a lot lower coupling. So, all can be handled in terms of understanding the absorption properties, but not inter-system crossing. That's not what's done. And not all conversion back to the ground state.
So just a short comment. It would be great if somebody would take the pain to do these kind of calculations on carotenoids, because the carotenoid community relies on 20-year-old papers to attribute spectral signatures to molecular symmetries.
Yeah.
And there's essentially a wild guessing going on what kind of states.
Yes. One of our aims for this year is to do CAM-B3 lip on such systems. We've already shown that density functional theory on a polyacetylene will give you the right geometry in terms of single and double bond lengths if you constrain the density functional theory to be a singlet ground state. With GGA functionals. With LDA functionals, you get an equal bond length in a metallic system. But But the ground state of polyacetylene with density functional theory is not a singlet, it's a high spin state, which is basically magnetic. So you can't calculate any spectral properties of polyacetylenes or carotenes with any form of reliability, because there's an entire manifold sitting underneath you at lower energy, and they interact with the states that you're trying to look at. And that's the basic cause of the problem. So these methods, I think, will get polyacetylene right, and that'll be the first time that density functional theory has ever been able to get polyacetylene correct. If that's the case, then we can do the carotenoids.
Yes, I think we better call it a morning there and break for tea. And I'd like to join me in thanking all the speakers.